Hi, this is a video in Unit 2, and Unit 2 deals with atoms and the periodic table. This video, I will try to explain what some of these numbers mean. Specifically, I'll go over atomic number, which is the number on top of each of these letters. Also, I'll look at the numbers that are associated with a specific type of isotope. An isotope or a pair of isotopes are atoms that have the same number of protons but different number of neutrons. So they are still the same element, they just weigh differently. The last number that I do want to talk about is if I take any of these isotopes, what is its mass in what's called an AMU, atomic mass unit. And here are some examples. These other numbers I will cover in later videos. Now, normally I would have this printed out, but my printer's on the fritz. But again, we are in Unit 2 of General Chemistry 1, and this topic, O2B50, are mass number and mass in AMU different, and also I'll discuss isotopes. Okay. The first definition that I want to go over is atomic number. And the symbol for atomic number is Z. And simply that equals the number of protons. Now, if we look at our periodic table, let's take phosphorus. We have a couple numbers. We have one in the corner, but sometimes that number is right on top of the letter, and we have a number with some digits after the decimal point underneath. Let me copy that for us. We have a 15 here, a P, and read it, 30.974. Okay. The Z, or the atomic number, is this one right here. Okay. Next, and again, we won't get to what this number is. We'll touch upon it, but we won't explain how to calculate until a later video. So the next thing is, before I do that, you want to remember that the number of protons, or the Z, identifies the specific element. All atoms that have 15 protons are phosphorus. The different isotopes of phosphorus vary in the number of neutrons. And that brings us to our next definition, isotopes. An atom with, or maybe I should put atoms, with same number of protons but different number of neutrons. We learned before that the nucleus is going to be consisting of protons and neutrons, except for hydrogen, which only has 1 proton and 0 neutrons. But let me give you a couple examples of now isotopes. And we will use hydrogen. And another way that you'll see elements written, specifically isotopes, if you're comparing different isotopes, is you'll have a number on the upper left and a number on the lower left. Don't get that confused with this number here. So this is literally from the periodic table in a box. But when we have something like this, whoever's writing this is trying to specify a specific type of isotope. This number now in the upper corner is different. This number is called the mass number. The mass number. Okay, and this is very important because this is where some confusion lies. Mass number should be a whole number, and it's always the number of protons plus number of neutrons. So do you see how if you know the number of protons, you know the number of neutrons if you're given what's called the mass number? I'll underline it. Actually, I'll circle all the good key terms. Mass number, atomic number, and isotopes. Okay. What about this? Oh, before we move on. So this is weird. The mass number is 1, which is the number of protons plus neutrons, but all hydrogens have 1 proton. All hydrogens have 1 proton. So what does that make the number of neutrons? The number of neutrons has to be 0 because the mass number is only 1. So this number down here is the number of protons. Now, yes, you could call it the atomic number, or you could call it the Z, okay, but we'll call it here the number of protons. Okay. Look at this. This is considered, some people consider this heavy hydrogen, because it's still hydrogen. Why? Because it has 1 proton. Now, make sure you switch over. The number of protons now is at the bottom. Okay. What is this 2? It's a mass number. So the number of protons, 1, plus some number equals 2. So there's 1 neutron for this hydrogen here. And this hydrogen's even heavier. So I'm not 100% sure. I use the term heavy hydrogen when I talk about this isotope. I'll give you names. I'll give them now. We know this type of hydrogen with what? 2 neutrons, right? This is how do I want to write this? 1 proton plus 2 neutrons equals 3. Okay. The name of this atom is tritium. Tritium. The name of this one is deuterium. And this one is called protium. How do I spell this? It has to be with an I. Protium, deuterium, tritium. They are all isotopes of hydrogen. Okay. Hopefully these terms are becoming more familiar. Alrighty. Just for practice, let me give you 2 isotopes of bromine, and I'm going to write it in this convention. Now bromine, one bromine can be this one, and the other bromine is this one. Now, when you're talking about isotopes and you're trying to convey what isotope you're using or studying, the way you want to pronounce this is bromium 35. No, not 35. 81. You go by the mass number. Bromium 81. So that's your pronunciation, or you'll see it written like this. So don't get confused. Those 2 things mean the same thing. Now, I know in this fashion, Br-81, we're not saying that it has 35 protons, but you should know it has 35 protons because all you have to do is look at your trusty periodic table. That's a given. Okay, so it's not necessary to write 35. All bromine atoms have 35 protons. And I want you, when you have time, to fill out this chart. For each one, I want the number of protons, the number of neutrons, and next, number of electrons. And electrons can be abbreviated E with a negative charge as a superscript. And I have to put a disclaimer, number of electrons when atom is neutral. So I'll make this easy. When the atom is neutral, you have to have the same number of electrons as protons, because protons, you could think of it as having a +1 charge. Electrons have a -1 charge. Now, I'm not telling you the charge in coulombs that You may know the charge of an electron in coulombs, the official unit, or the SI unit of charge, but instead I'm giving you numbers that will help us decide later whether an atom is positively charged or negatively charged. We're just going to consider a proton as a +1 and an electron as -1. So the answer for the protons for bromine is 35, and then when the atom is neutral, we have to have the same number of electrons. So it's your task now to fill in 1, 2, 3, 4 slots. Okay. If we have time, we'll go over the answer, but I think you can handle that on your own. Next topic. We know mass number, right? Mass number, and let us put a check. Okay, and put an example, 12,6. Okay, so that's carbon, and that has a mass number equal to 12, right? It's the number of protons plus neutrons. Mass number equals 12. It's a whole number, right? You can't have really half a proton or 0.35 neutrons. But there's this other term, and I'll put it versus. The other term is atomic mass unit. That was another row in that cover slide. And the atomic mass unit typically has numbers after the decimal. This is abbreviated AMU. Okay. Let me give you the definition for atomic mass unit. We already know mass number, protons plus neutrons. Atomic mass unit, or AMU, has a defined meaning. So 1 AMU is defined as 1/12 the mass of a C12 isotope. This is the same thing as writing the isotope like that. Okay? C12, just like we had Br81 on the previous page. Okay, its definition of 1 AMU is 1/12, but you notice that the mass number is also 12. So in this case, the mass number and the atomic mass unit, or the mass in AMUs, are the same. Therefore, let me write this down. This isotope equals 12 and it's a definition. We're going to give ourselves maybe 3 zeros past a decimal point. Okay, technically it goes on and on, 0, 0, 0, 0, 0, 0, etc. Make sure you put the units. Now, I know it looks kind of redundant. Well, isn't that just the same as the mass number? Isn't the AMU mass the same as mass number? Only for carbon is that true. Okay, because if you look at the cover slide real quick, you notice that for the other isotopes, the AMU does not exactly equal the mass number, right? The mass number, again, is protons plus neutrons. So 11, but here it's 11.009. Oxygen is 16 mass number, 8 protons, 8 neutrons. But the AMU is 15.995. I'm going to try to explain why that is the case. Okay. That is the case because one AMU has a specific, a proton has a specific AMU value. This is going to look a little strange at first, but I'll show you how we could resolve those differences between the mass number and the mass using AMU. So I lost my spot. don't put 1 here, mass of 1 proton. Now, if you were looking at this definition, you would imagine that, oh, a proton is worth 1 AMU, a neutron is worth 1 AMU, we get 12 protons plus neutrons, 12 AMU. But technically, the mass of 1 proton equals 1.00728 AMU. So that's kind of strange. I thought since AMU is 1/12 of this, a proton should be 1 exactly. Let me show you the mass of a neutron. That's also not exactly 1. It's 1.00866 AMU. And then even an electron, it does have mass. I think initially students are taught that electrons are massless. Well, yeah, they're very, very tiny, but they're not technically massless. Mass of 1 electron equals 5.486 times 10 to the negative 4 AMU. Okay, so it's 0.0005 AMU. Okay. Now, well, if that's the case, and you have carbon with 6 protons, 6 neutrons, and electrons that we could ignore the mass because it's so low, wouldn't we have more than 12 AMU? Yeah, we would have more than 12 AMU. So where is the reasoning, or why is there a discrepancy? This is what I found out. A small amount of the total mass, or of the predicted total mass, right? With 6 protons and 6 neutrons, you would imagine that the AMU would be 12.0 something, right? Because it's not exactly 1. A small amount of the predicted total mass is converted into energy. And it's a special type of energy. It's called nuclear binding energy. Okay, I'll underline that. And that is the energy that is released when a proton and neutron come close together. So this is of the nucleus. Can that really happen? Can mass be converted into energy? Well, you are familiar with Einstein's E equals mc squared. So yeah, a certain amount of energy is used to help bind the protons and neutrons together, and that equals a certain mass. And if you want to think about it like this, the E is known as the binding energy. My class won't have to calculate any binding energy. We won't even have to know how to convert binding energy into mass, or how much binding energy there is in an atom of whatever. But this is, I like how they call this M. They call this M now the missing mass, because, again, you would expect that the mass in AMU for carbon would be more than 12, a little more than 12. But we have that missing mass. So this is the missing mass. Okay. Okay. Let us take one more glance at the cover slide, because for some of those, actually, technically, there's missing mass for all of them. There's missing mass for all of them, but sometimes we're missing enough mass that we actually go under, right, the mass number. Like for this case, it's not 16, it's lower than 16. Okay. Now this is higher than 11. That's because the theoretical, when you look at the mass of a proton and a mass of a neutron, would be more than 11.009. And then because of that missing mass, for the binding energy, we knock it down to 11.009. And they can look at this experimentally, or measure it experimentally. So is that kind of understood? The other thing is that because we are defining, right, we are defining an AMU as 1/12 the mass of a carbon, that's why this is exactly 12.000, because 1/12 of a carbon is 1 AMU, and this has a total of 6 protons and 6 neutrons to equal 12. Okay. Again, the actual number, this does also have missing mass, right? Because when you look at our numbers here, okay, theoretically, that should be a little more than 12. But again, we have this missing mass. All right. Is there anything else I want to say? No. Just be aware that it's close. The mass number is close to the atomic mass unit mass. All right. Let me actually give you the answers though for this table. The number of neutrons would be 79 minus 35. Oh, math. So that is that really 44? My math right? 44 neutrons. Now, since this is bromine, it has to be 35 protons, and since it's neutral, it has to have 35 electrons. And now here, the number of neutrons should be 46. It seems a little high, but let me just double check. Carry the 1, yeah. 44 neutrons and 46 neutrons. Alright, in later videos, we are going to look at what these numbers mean. These with 5 significant figures. It's close again, right? It's kind of close to the to the atomic mass. Oh, it's not the atomic mass. The mass number of each of these isotopes. See, 10.806, 11, 12.009, 12. And what else? Also, we are going to look at what's called percent abundance. Okay. Now, that will just tell you what percent of, for instance, nitrogen in the universe is the isotope N14, 99.6. So there's another 0.4% that's still nitrogen, but different isotopes of nitrogen.